So now that we're talking about exponential functions, we are going to bring up another number that we haven't talked about before. It says, so there are many numbers in mathematics that are more important than others because they find so many uses in either mathematics or science. Good examples of important numbers are 0, 1, I, and pi. In this lesson, you will be introduced to an important number given the letter E for its inventor, Leonhard Euler. We're looking at the letter E. This number plays a crucial role in calculus and more generally in modeling exponential phenomena. So kind of weird, we use this letter. This letter is not considered a variable. We will be working more with E in the next unit. Today we'll just be graphing the function y equals e to the x. Now, just if you were on your calculator and you look around, you'll see a little like lowercase e. You'll also see an e to the x button. And e, it's irrational. Okay, so it's a decimal that doesn't end or repeat, but it's about 2.718, just like we could say that pi is about 3.14. So first we're going to find the inverse of e to the x. We're just going to look at its graph it on the calculator, and see what it looks like, and then we'll be getting more into it this unit and next unit. So here, if I switch x and y, I get x equals e to the y. And then we have that same necessity to put it in log form. So I will label, because I know we haven't done this as much this lesson. So this is base to the exponent equals a number. And we want to go to log base b of a number equals the exponent. So labeling this, it's a little bit in the different order, but this is the base, this is the exponent, this is the number. So when I write this out, I'm going to write log base e of x equals y. Now, not to throw too much at you at once, but basically we already talked about how the common logs, log base 10 of x, we don't need to write the base. This logarithm, log base e of x, is actually so common once we start to get into exponential modeling and calculus and things like that, it has its own special name. And this is just another math shortcut. People didn't feel like writing log base e of x, so they called it ln of x. So that looks like it could be in x. It's weird because it doesn't have the word log anymore as a shorter word, and this just stands for log natural because they say e is the natural base and ln is the natural logarithm. As I said, more to come on that. So down here on our calculators, we are going to be graphing y equals e to the x and y equals log base e of x, which we know can also be written as ln of x. So this is definitely one you have to do in your calculator because e is not something that I know powers of. So if I go on my calculator and I find that e to the x button, I'm going to write down that same values of the table that I did for the other one. We're going to round to the nearest tenth here for the powers because we're going to get decimals, of course, and it's not helpful to graph. So e to the negative 2 is 0.1. E to the negative 1 is 0.4. This one is not going to be anything to the 0 is 1. And as I said, this is coming directly off the calculator. To the nearest tenth, e to the first is 2.7. And then we have 7.4 and 20.1. We're actually going to just take those x's and y's and switch them. There's also an ln of x button on your calculator, so you could actually just graph it. But here we're practicing just switching those x and y's. So this graph would be 0.1, 0.4, 1, 2.7, 7.4, and 20.1. And over here we're going to have negative 2, negative 1, 0, 1, 2, and 3. Now, these graphs are going to look super similar to the ones we did for 2 to the x and log base 2 of x. We'll see there's some little differences. So I'm just going to start to graph those points. Instead of being 1, 2, we have 1, 2.7. Instead of being 2, 4, we have 2, 7.4. And basically the base is just larger here. So e to the x will increase more quickly for the values that are greater than 1 or greater than 0. So here is the graph, just a little steeper. And over here we have 1, and then 0, 1, and then 2.71 and 7.42, which is a little bit off the graph, so I'm just going to put that there, and you'll see the same shapes. If I did all those questions about domain and range and end behavior and all that good stuff, I would get the same answers with these two functions. Now, we're going to do a little bit of evaluating with ln of x now that we've learned what it means in terms of a logarithm. So this is more related to what we did yesterday. So it says, without the use of a calculator, determine the values of each of the following. So when I see ln of e, that's like saying log base e of e, because ln means log base e. So what exponent for e gives me e? That would be 1. Just like if I had log base 3 of 3, what exponent for 3 gives me 3? That would be 1. If the base matches the number, it's always going to be 1. The next one, and you don't have to rewrite these, I'm just rewriting them because you're just starting out. So what exponent for e gives me 1? Well, what exponent for anything gives me 1? That would be 0, right? E to the 0 equals 1. The next one I'm going to do without rewriting. When I see ln, I know it means log base e of e to the 5th. So what exponent for e gives me e to the 5th? That would be 5. And what exponent for e gives me e to the square root of e? That would be the 1/2 power. Our last little topic in this lesson, and all of this graphing we're going to be practicing more, and especially these transformations we're going to be doing, we'll be practicing more in the next lesson. It's just kind of like intro today. It says, we talked about this at the beginning of the last lesson, but there are many different parent exponential and also logarithmic functions. The same transformation rules you learned in Unit 5 can be applied to these functions. So as a reminder, parent exponential functions are in this form: y equals b to the x, where b is greater than 0 and b is not equal to 1. So these are all examples of parent exponential functions. 2 to the x, 1/3 to the x, e to the x, 10 to the x. They're each kind of their own parent function versus most other functions we've seen that just have one parent function. Parent logarithmic functions are in the form y equals log base b of x, where b is greater than 0 and b is not equal to 1. So here we have, and I just did inverses of each of these to show it doesn't have to be, I could have listed whatever for my examples of parent functions, but these are a few here. We see the natural and the common logarithm here. So here are your rules, and for this lesson or this unit, we're going to also start to introduce the horizontal compressions and stretches, which are the two that we did not do last time. We really get a lot into those when we do trig, but for now, we're just going to see how they work. So if you look at the horizontal compressions and stretches, and you should look through all of them just to refresh your memory, if I change where x is with multiplication, that's going to be a horizontal compression and stretch. Versus our vertical compressions and stretch, where we put a number in front of the function. So if we put a number in front of the function, it works like normal. A big number stretches things, number greater than 1. A number between 0 and 1 compresses things. We know when we're inside that parentheses with x, just like left and right, it works backwards. So if the number is greater than 1, it actually compresses it horizontally and presses it in more towards the y-axis. And if we use a number that's smaller, it actually stretches it away from the y-axis. So I said, right now we're more just writing them, but we will get more into it with trig. So here are two parent functions. We have 3 to the x, we have log base 5 of x, not inverses of each other, but both examples of parent functions for exponentials and logs, respectively. So if I want to reflect in the y-axis, I'm just going to write these rules as a refresher. That would be f of negative x. Shift left 3 would be x plus 3. Down 4 is minus 4. A vertical stretch of 3, followed by a shift right 5. 3 in the front, x minus 5 in the parentheses. A horizontal compression of 2 just means wherever the x is, I put a 2. So we don't do anything different like make the 2 a 1/2. We just recognize that if I'm multiplying the x by 2, it's actually going to compress it or press it in by a factor of 2, not stretch it out. So looking through our 3 to the x, this one should be 3 to the negative x. I'm going to make wherever x is negative. This one is going to be where the x is, up in the exponent, x plus 3, and then minus 4 tacked on the end. Here, I'm going to put a 3 in the front, and then I'm going to do 3 to the x minus 5. Parentheses are not really necessary because the exponent would happen first anyway in PEMDAS, but I put them there. And then this one is 3 to the 2x. So right where the x is, I make it 2x. Over here, changing the parent logarithmic function, it is kind of tricky. Like that 5 is just there. I know it's in a weird spot, but when we make our changes to x, they're going to happen where the x is, which is in that number after the base. So the base is not really going to change at all. So here, this is log base 5 of negative x when I plug in a negative x for the x. This one is log base 5 of x plus 3 minus 4. This one is 3 times log base 5 of x minus 5. And this one is log base 5 of 2x. So in your homework, you have a chart going over those, and it's really just using the same transformation rules plus that extra one and plugging things in the correct spot.